Let's wait for 5 more minutes to see if other people join. Then we'll start at 3:05. Okay, so let's begin. So again, welcome everyone. This is NOC24 W139 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudev Das Gupta. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar in this institute. So as you know that we have already completed 12 weeks of the course, and also the tutorial sessions are also completed. So this is something add-on to whatever we have discussed so far, right? So as you have noticed that since 2021, the syllabus of your competitive exams and entrance exams have been updated. So you need to have some basic some advanced understanding of some of the basic concepts. Okay. So keeping that in the view, so we will be going to discuss the following topics. So this is summary session. So it will be more of like we name it summary session, but it will be more of like an add-on to whatever we have discussed, right? So the topics that I have planned to discuss today are basically, as we have promised in our last session, that will be a little more, it will add a little more depth to whatever we have discussed in the last part of the last session, that is day before yesterday. So we'll be looking into memory hierarchy and the reason behind this memory hierarchy, right? Means that what is it and why is it? Then we'll be discussing briefly on your SRAM, 60 SRAM more specifically, and the operations for, let's say, hold, read, and write. Same we'll do for your 1T1C DRAMs. Okay. And we'll explain to you that what is the dynamic part, what is the random access part, what is the memory and everything, right? What is volatile, what is non-volatile. And then we'll conclude our discussion today by looking into the scaling theory that was very early in 1970s. It was proposed by Robert Dennard, who was a IBM fellow. Okay, so remember that IBM had played a very key role in the early development of the semiconductors, okay, along with your Fairchild, Intel, Texas Instruments, etc. So, and also we'll just touch upon, and just for your information's sake, we'll be telling you that what are the key innovation that helped or aided in FET or field effect transistors miniaturizations. Okay. So let's begin. So memory hierarchy. Okay. So when you open a laptop or a mobile phone, what you see inside is this, or in other sense, any computing environment. You see basically to start with, what is basic pillars of your modern electronics, basic pillars of modern day computing environment. Okay, what do you think? So one, obviously you know that logic has to be there. That is the key block of your processing environment. Another thing, you need to have memory, right? Remember the von Neumann architecture you have been studying since childhood, that you keep your processing separate, or your, let's say, your ALU separate and your memory unit separate, and then you have a buses or wires connecting both the things, or channels connecting both the things to fetch the instruction sets and everything from the memory block, and you fetch it to the processor where the processing happens, and then the results are stored again back to the memory block. Okay. So there are now very interesting things coming up in modern day research, like your in-memory computing, right? As we will see that memories are nothing but your, you can say, the matrices, right? Last day we also see that row, how the 2D space of the memory array behaves, right? So in those kind of arrays, as you can see, as you know that most of the computing environment depend on your multiplication, addition, kind of operation, or your, let's say, matrix products. So these memory elements can be used to do some sort of computing at the memory place itself, right? So that is what is reducing the latency for fetching the data from, or instructions from, memory to the processor. So those things are coming up. Those are called in-memory computing. Okay, a heavily researched topic in today's scenario. So logic, memory, and what about the other things? Other and very important thing actually, which derived, which actually pushed the innovation in the electronics at the very beginning or the early days, was this communication, right? So it is very surprising. It's not very surprising. It is very distinct to see that in your early stage, like your Bell laboratories, right? They used to heavily research on the communication aspect of the society, right? You need to, this Graham Bell's invention on the telephone, and then subsequently computing environment developed to aid the communication thing. But nowadays, what is happening? Your due to the industry revolution in the semiconductor department, semiconductor domain, your computing power has been so high that this semiconductors, or your computer electronics, is basically deriving the communication, right? So, for example, do you need your 6G? Just think it in this way. So, what is the difference between 5G and 6G? So if you reduce those aspects of a large beam forming and every high-end stuff from the basic user's point of view, does it matter if your video gets downloaded at 1 nanosecond or 1 microsecond? It doesn't matter. It doesn't matter to a common user, right? To the end user. But again, there are other aspects which is basically developing the society. It is doing, it is being done for the development of the society in multiple aspects, like your this invention in artificial intelligence and all are doing really good in your medical research. It is, you must be aware of these things. So these are the basic three things which you still require in today's computing environment, right? Logic, memory, and communication. So if you see any block, you will see processor unit, right? Your microprocessor unit. And let's say, for the sake of it, we write it multi-core. Then you will have your main memory unit. Okay. Then let's say you have your solid state drive, right? SSD. So this is basically your RAM. Okay. And other part of the stuff, basically this, I mention it as other parts. That is, let's say, your, what can it be? Your communication have what? Wi-Fi, Bluetooth, 5G, 4G, GSM modules, right? Switches, duplexers, LNAs, then low noise amplifier. LNA means low noise amplifiers, power amplifiers, RF front-end modules. These three things are called basically RF front-end modules, filters, everything, right? Those comes into the communication block. Then you have your PMIC, we call it power management IC, because how to the static power and supply of the static power dissipation we have discussed in our earlier sessions, and how to distribute the power supply so that the effective usage of the power gets reduced or managed efficiently. That is controlled by this stuff. Then you have your mechanical components or some piezoelectric components, etc. Okay, so basically, and between them they have this memory buses or your wires, basically channels, memory channels running from processor to the main memory and then SSD, etc. Okay, so what are the basically purpose of this thing? Purpose is to, there are two faceted thing, right? One is your latency or delay in, let's call it, memory unit to core or the processor. Okay, we want it to reduce, right? Because we want fast operation. The performance of your processor or the speed of your processor will be largely dependent on that, how fast you can fetch the instructions from the memory. Okay, that is a big bottleneck in today's scenario. Your processors can work much faster than, but this fetching becomes a bottleneck. Okay, then another thing which is very important is the capacity. So capacity or memory size, you want what? You want as large as possible. Okay, so what is happening basically, let's say to perform the entire application of your all the computing application and all whatever you can do with a mobile phone, you want to have a single memory unit, and that you want for a large capacity and very fast. Okay, but that is not possible always. And for example, capacity or memory size depends on how small you can make the fundamental elements. Let's say if your transistors are the fundamental blocks of the memory organization, then you need to make your transistor smaller and smaller, right? So, but again, you know that your delay, let's say TD, reduces when your resistance reduces, right? And your resistance reduces. How your resistance reduces? By reducing your R on of the transistors, and for that you need to have your W by L higher, or let's say area higher. Okay, so if you have your area higher, so then your capacity becomes lower. So you can see that this is desired, and that desire leads to something which we do not desire. Okay, so this is intertwined. So this kind of problems can be solved by having a memory hierarchy, or you break down the memory into multiple blocks and make the required amount faster, and the remaining amount what is not required, you can make it slower but of a larger capacity. Okay, so your bottom line is distribute the entire memory into small blocks and then make layers, or let's say, let's not call it layers, make some of them fast, low capacity, and remaining slow but high capacity. Okay, fine. So how do we represent that? This idea is represented by something called memory hierarchy. Okay, so from whatever we have discussed so far, so we can conclude two, three more points, right? First one is that the memory closer to processor has to be very fast, right? For obvious reasons, because that is where the instructions will be saved and instructions are needed to be fetched out. And the memory away from processor can be a little bit slower. Okay, so how do we distinguish that? We represent that in the last class we have seen this diagram. So this is, let's say, L1, L2, L3, last level. Then you have your main memory. Then you have your solid state drive, and then you have your hard disk drive. Okay, so and where does the processor lie? Processor lies at this place. So what we do basically, this till this much we make it coexistent with the processor. Okay, so this is, by the way, these are called cache memories. Okay, so what are these made of? These are made of your SRAMs, which is the fastest memory block you can have. Okay, or sometimes embedded DRAM. We'll discuss about these things. Okay, so this entire thing is coexistent in the processor itself. So if you let me just highlight this part. So if you just open a processor, let's say it is some kind of multi-core processor. Let's say this is some IO blocks, okay, which is not of interest to our this discussion. And let's say we have total 8 cores. So this is core 1, core 2, core 3, core 4, core 5, 6, 7, and 8. Okay. So, and let's say these are, and what else should be there in the processor? Obviously, you need to have some control circuits. Okay. Fine. Now, where does this cache memories lie? So your these blocks, let's say these are L1 cache. Okay. So every core has their dedicated L1 cache. Okay. And then let's say this is your L2 cache. Similarly, every core will have their dedicated L2 cache. These are nothing but your SRAM arrays. Okay. And then your L3 cache is generally shared between all the cores. This is your L3 cache. Okay. So this is how, and this entire stuff is your microprocessor. Manufacturers are your Intel, AMD, Qualcomm, etc. Okay. So you see, so from this understanding, can you tell me that, can you just think for a second that which of the, so the question is L1, L2, L3 all are made of SRAMs. Okay, that means made of some MOSFET blocks. So can you tell me the area of MOSFETs of L1, L2, and L3? So which of this level 1, 2, 3 cache should have the largest size of the transistors? Just pause the video and think for a minute. So if you have guessed that, what happened? So if you have guessed that L1 cache has the highest, largest size of the transistor, you are absolutely right. That is because layer 1 cache is directly at very close to your core or the ALU. Okay, ALU of the core. So it has to be the fastest. So L1 is fastest. Okay, that means ion has to be highest. That translates to W by L of these transistors has to be highest. So your W by L of L1 will be greater than W by L of L2, W by L of L3 MOSFETs. Okay, that MOSFETs used to make the SRAMs of this cache memories. Okay, so this is important to understand. So we can conclude that. Okay, just let me use this one. So as we move up the ladder, my capacity reduces, speed increases. Okay, so these two we have to remember very carefully, or we have to understand why this is happening. Okay, and then what about your main memory? So this block is the YOLO stuff we have discussed. And let's say this main memory is the green one. Okay, so this is your main memory. So this is basically made of with your DRAMs, okay, or dynamic RAMs. DRAMs are DRAMs has access times, or the time required to access any instruction from DRAM to your processor, or you, let's say, in other words, you can also think it of in the read and write times, around 20 to 50 times slower than your SRAM. Okay, and there are other distinguishes also that we will look into. So DRAMs are basically dynamic random access memory. Okay, so and SRAM stands for your static. So this things we will explain later. Random access means you can access each bit. Access means your read write each bit individually. Okay. And what about your solid state drives? Solid state drives are nothing but your these things. Your the memory or the uh, non-volatile part of your memory in the device. For example, if you buy a PC or a laptop, you talk about, right, 1 TB memory, 2 TB memory. So that part is being offered by your solid state drives. And hard disk drives, earlier it was used, and then these are the magnetic drives. Okay, so this is basically your 2D and 3D NAND flash memories, and these are basically your magnetic memories. Okay, so let's draw a line. So below this is your volatile memory, and beyond this is your non-volatile memory. Okay, so if you have understood this much, so you need to understand another thing, that why so much research in memory. Why people are researching so much in memory devices, new topologies, new architectures, right? So, what is the need of today is that, let's say, 21st century, what are the things that is driving the requirement of this huge memory, uh, let's say, revolution? One thing is that your AI, okay, then your big data, for example, AI. Why? Because any artificial intelligence or machine learning models you require, if you are aware of that, you need to train the weights, right? For training, you need to have a large amount of test data. Okay, you need to have a training the NNs or neural networks. Okay, then big data, for example, real time monitoring. Okay, then you need to have, let's say, video streaming. Then in multiple industrial applications, right? For example, if you talk about railways, so they monitor every aspect of the signaling involved in that on a real-time basis. So that is a huge chunk of data. Okay. And you top it up with your video streaming like CCTV footages and everything, or surveillance, let's say, or let's say your supervisory control and data acquisition, for example, your SCADA and every stuff, right? So those require huge amount of data to be stored and processed at the same time. So you need a huge amount of data in today's scenario. So thus you require a huge amount of memory. Okay. So people are exploiting, and also the with the scaling of processors, your this scaling of your, what you say, this is called the memory wall problem. Okay, so we'll discuss it in short time, in a short time, that the way your core speed or performance is increasing, your memory's performance is not increasing. So that is leading to innovation of multiple other types of memories. Okay. So what is a memory basically? Memory is nothing but storing your binary digits, right? Bits or zeros and ones, right? Zero means a on state, zero means a off state, one means a on state. That means on and off means, let's say, your high resistive state and low resistive state. So you need to basically segregate on the same device two distinct states. If you can achieve that, that is simply a memory. Okay. Now you need to have to understand what are the energy aspects, what are the delay aspects, how fast you can read, how fast you can write. Okay. Those will determine the how good or bad the memory you have come up with. Okay. So people are researching in this area what they call, you know, storage class memory. So it falls between your DRAM and NAND flash. So they call it storage class memory. Okay, so what are the things? Let's say you must have heard ferroelectric memories are coming up here, then phase change memories are coming up here. Okay, RRAMs, resistive random access memories, etc. So this just you should be aware about the nomenclature of these things, as it is a UG course intended mostly for the UG students. So maybe you do not need to understand what ferroelectricity means at this point, but you should be aware of that these things exist in today's scenario. Okay. So having said that, then I was talking about this, right? The memory wall problem. Okay. So what is happening basically, if I just plot the performance in, let's say, we can take off any types of your okay, how many flops of operation you are having per second, okay, those kind of parameters, and this is the year. So you will have these two distinction. Okay, this is the core and this is your memory. So you can see that there is a huge gap between how your core has been developed throughout the years and what are the you know deficiencies the memory or the memory is falling behind. Okay, so this is an issue which we need to address basically. So the issue is that our processors our processors can operate very fast, but memory interface and capacity is becoming the bottleneck. Okay, so that is a cause of concern for which a huge uh, boom in the research in these memory devices have been going on. Okay, so or from the another thing, from the energy perspective, you should also know this figure, that it will be surprising for you to know that for a for a modern day chip, 95% of the energy is being used by the memory energy. Okay, and for example only 5% will be your compute energy. Okay, so that is the scenario today. So you need to understand that your energy is also an important parameter to determine which are the memories you should go for. If you can even reduce some femto joules per operation, that will also help you to get into somewhere and make your idea to a product level very soon. Okay. So now let us discuss about the memory array. Can be 2D, 3D kind of array. We'll discuss 2D array. Okay. So basically, let's say you have multiple address lines, and let's say you have this column decoder, okay, and it decodes it to k bits, or let's say k equals to 8, so you'll give a byte, right? Then you have this sense amplifiers and other circuitry, okay, and in this case you have, so these are the input lines 0 1, let's say n minus 1. This is, we call it row decoder, okay. So let's say this is 0 1 to m minus 1, okay. So what is the number here? This number is 2 raised to m, okay. What is this number? This number is k times 2 raised to n, okay. So these column lines are called your bit lines, okay, or your BL. So this number of bits, and this are called your word lines or your access lines, okay. These are used to access that particular row, okay. And at these locations are basically your memory elements are sitting, okay, in all of these locations. So these are the memory elements, okay. For example, if you talk about and to mention it here, that you can access k bits, access group of k bits at a time. So your quanta is k bits, okay. If k is 8, you can access 1 byte at a time, okay. So now, how does this look like in the real scenario? For example, this is your word line, this is your bit line, okay. Let's say this location, okay, this location we want to see, okay. So this is your word line. So let me just use the proper color coding. So this is, let's say, your word line, and this is, let's say, your bit line, okay. So how will your this device will sit upon? So your word line, this is your bit line, and let's say this is your capacitor. So this is basically your memory cell, okay, 1T 1C DRAM. Fine. So this block will be connected between the every intersection of the word line and bit line. So this is how your memory array is made of. So to note another point, that sizing of memory elements depend on sizing of your memory element depend on let's say layout of the memory. Okay, and it is done in a function of f square. What is f? F is the minimum feature size of the technology. Okay, that means the minimum width of the metal line you can draw on a through the lithography process. Okay, for a particular technology. So let's see about DRAM. So this is basically your DRAM. Okay, so your DRAMs will have a your this dimension is around 2f 2 feature size, and this direction dimension is around 3 feature size. So your DRAM is generally having a size of 6f square. Okay, and what about your SRAM? Your SRAM will look something like this. So this is your bit line, this is your bit line bar, this is your word line. So these are the PG or pass gate transistors. Okay, and then you have the back-to-back connected inverters or cross-coupled feedback connected inverters. Okay, so in SRAM's case, depending upon in which layer it is used, level 1 cache or level 2 cache or level 3 cache, its size depends on this 20 to 30 F this side, and this side it depends on 7.5 to 10 F. Okay, so it basically gives you an area of 150 to 300 F square. So you can see, right, that your capacity of SRAM has to be lower to accommodate higher speed on the same area, right? Because it needs to have a larger W by L of the transistors. Or it needs to have a fatter transistors, okay? So that is DRAM, that is SRAM, and for your 2D NAND flash. So NAND flash is nothing but a transistor where your there will be a charge trapping layer or the floating gate. Okay, these concepts are maybe a little bit advanced for you, so I'll just keep this one in our next detailed discussions. But understand that whatever the solid state drive you are using today, or SSD, what you will call it, those all are made of your 3D NAND flash. Okay, this is how your 2D NAND flash looks like, and it will have a feature size of, let's say, 2f, and then this way it is 2f. Okay, so it will have a 4f square kind of stuff for a single level cell. And for 3D, you will have 4f square by n, where n is the number of layers. Okay, So I had earlier asked you to look into the branch education's channel for more detailed visualization of this kind of stuffs, right? So how the actual things look like. These are all the circuit schematic, but actual things look something very different, okay? So you should go to that channel and look into the architectures of the NAND flashes, DRAMs, SRAMs, etc. Okay. So you need to have, let's say this is your memory block, okay? Your memory block will not only have memories, okay? It will have pure memory cells and some peripheral circuits, okay? What do we mean by peripheral circuits? For example, your sense amplifiers, okay? Sense amplifiers are come into the domain of peripheral circuits, peripheral circuitry. So your there is something called array efficiency of the memory array that is defined by, as you have understood this, let's say a area of M, this is area of P. So AM by AM plus AP times 100%. So this also is a very important parameter, you know. For example, I have seen many multiple research papers where they claim that they have shrunk the area of the memory cell, okay? But to access that, you need to have a very large peripheral circuits, okay? Maybe you have reduced the area on this memory cell, but you are compromising with this peripheral circuitry, okay? You need to have large cells, amplifiers, ADCs, and whatnot. So a proper performance indicator can be your area efficiency, array efficiency of the memory array, okay? So this is what we will discuss till this memory hierarchy and all. And in the next stuff we'll be going to SRAMs, okay? So let's take a 5 minutes break here. Okay, so let's resume. So SRAM, we have seen that it looks something like this, right? So this is your word line, this is your bit line, this is your bit line bar. You will have something like this. Back to back connected inverters. Excuse me. So these are your pass gate 1 and pass gate 2. This is your inverter 1, this is your inverter 2, and let's call these nodes N1 and N2. Okay, so note that N1 and N2 are the storage nodes. Okay, the parasitic capacitances at these nodes stores the charge. By that mean it stored the memory or data. Okay, BL and BL bar are the bit lines. WL is the word line. Okay. Now let us expand those inverters and see. Let me draw it a bigger picture. So this is your inverter. So that is the another inverter. Okay. Now a pass transistor is connected to this and connected to this. Another pass transistor is connected to this, and this. Okay, so you have your word line flowing down here. Always note that your word lines are connected to the gates of the transistors. Okay, that is basically it controls the on and off operation of the transistors. And if this is your word line, these are the bit lines. Okay, so this is your PL, this is your BL bar. Okay, let's call this node to be N1 and this node to be N2. Name of this transistor is pass gate 1. Let's say pass gate 2. Let's call it pull up 1, pull up 2, pull down 1, pull down 2. Fine. So that is how your 60 SRAM cell look like? So what are the possible operations that can happen in your SRAM? One is your hold operation, means it just holds the data, okay? Then your read operation, and write operation, okay? We'll see how these three things happen in your. I just copy this stuff, copy, add another page, okay? So we'll see now. First, hold operation, okay? For hold operation, make your word line to 0. That means make it 0. So this will be 0, this will be 0. So this transistor will be off, this transistor will be off. Fine. So now what do we have? Our circuit becomes simply this, right? So this is your N1 node, this is your N2 node. Okay. So whatever is stored at N1 and N2 will be kept held. Okay. So if N1 is kept at 0, so N2 will obviously be at 1 via this transistor, and if your N1 is at 1, N2 will be at 0 via this cross coupling of this transistor. Okay, so this is basically cross couple feedback of the two inverters stores or holds the value. Okay, values at node N1 and N2. Fine. So that is how your hold operation takes place. Now we need to, let's say, uh, look into the read operation. Okay. So again, we'll just paste the circuitry. Not sure. Okay, just let me move it a little bit up. Okay. So what are the steps? So why don't I make this a little bit smaller than, okay. So let's say N1 is having 0, right? And N2 is having 1. That is already stored in these two nodes. Okay. I want to read what is stored in the BL. Read the stored values 0 and 1. Okay. So what is the first step? Pre-charge BL and BL bar to VDD or 1. Okay. That means let's say you charge it to 1. Both of them you charge it to 1. Okay. Now make WL equal to 1. Okay. Now you make WL equal to 1. That means this will be 1. This will be 1. And this was 1. This was 1. Okay. Now what is the condition on the transistors PG1 and PG2? Check conditions on PG1 and PG2. Okay. So this is conducting, but this is off because gate to source voltage for an NMOS, we know that threshold voltage is greater than 0 generally for an N plus poly P type substrate NMOS. Okay. So if you have your gate to source voltage 0, that means your transistor is off. In pass transistor, if both ends, drain and source, are at the same potential 1 1 and G also at 1, gate also at 1, so the transistor will be off. So PG2 will be off. Okay. So now what is happening? And what about your, so this is on, and what about your this networks? So this one is 1, right? So similarly, let's say this is 1 and this is 0. So this is 1 means your this is off, and this is 0 means this is off, and let's say your this is on and this is on. Okay. So what is happening basically? You have a discharge path or of the BL. So BL discharges and N1 charges. Okay. So what is happening? Voltage at N1 increases, node 1. Voltage of BL decreases. Let's say it decreases from VDD to VDD minus delta V. Okay. And let's say this is your delta V. And what about your BL? So this is becoming 1 to 0 and this is remaining 1. So that means if I use a sense amplifier, so this is now VDD minus delta V and this is now VDD. So the difference amplifier will show me what? This will give me amplification times minus delta V. Okay. So by checking sign of the SA is sense amplifier. By checking the, just like an op amp for example, or a differential amplifier, any sort of differential amplifier you can use. By checking sign of the sense amplifier, one can determine if BL, if your N1 was 0 or 1. For example, if output of SA is negative, so N1 was storing 0, and output of SA is positive, the way we discussed, N1 was storing 1. Okay, so that is how you read what is stored in the SRAM cell. Fine. Now if we are going to look into write operation. Okay, so let me just copy the cell. Okay, let's say you have 0 present at this and 1 present at this. You want to write, we want to write N1 to 1, N2 to 0. Okay, so what will you do? Pre-charge BL with 1, BL bar with 0. Okay, so that means what you are doing, you are making it 1, this is making it 0. So this is 1, this is 0. Fine. Set WL to 1, you are setting WL to 1, this is 1, this is 1. So what is happening now? This is also conducting, this is also conducting. Fine. Okay, so node voltage at this point, this node voltage, let me show it with green, node voltage increases. In this case, node voltage decreases. That means your 0 is turning to 1 and your 1 is getting to 0. Fine. You understood, right? So a thing to note here is that BL bar plays an important role. In earlier case, this right hand side was completely not useful at all in that sense for conducting. Okay, so that is how you write into an SRAM cell. So this is very basics. There are some advanced concepts and nitty-gritties involved, or the trade-offs involved when reading and writing, and how the capacitances come into picture that determines the glitches in the timing diagram, or in the hold state of the SRAM, how the butterfly curve, so-called butterfly curve, is obtained, and that helps to hold the value. Okay, so those part I am not discussing because that is a little bit advanced concepts, but you can grasp if you want to. You can refer to some courses that I'll recommend on the comment section of this video. Okay, but I think for your gate exam purpose and in that regard, this much is sufficient. So now coming back to dynamic random access memory. Okay, so 1T 1C architecture. Okay, so let's say this is your word line, this is your bit line. So I have just drawn it in a flipped version so that you understand. If in question you are given word line like a vertical line, you should not get confused. Okay, so how do you write to this? Make your WL equal to 1 if bit line equal to 0. If bit line equal to 0, what will happen? Let's say this is on, that means a channel is formed. Now if your bit line is equal to 0, whatever is storing in the capacitance will, this bit line is, let's say, 0, so whatever stored in the capacitance will go directly to ground. So that means, by the way, this is the N or storage node. Okay, so N will be 0. Now if your word line is 1 and your bit line is 1, so obviously the reverse thing will happen. If bit line is 1, it will charge the capacitance and your N potential at N becomes 1. Okay, this is how you write values. Okay, and how do you before that, let me just tell you that this capacitance is not a discrete one. It is made using using trench cell, where it is under the substrate of the same transistor, thus making it area efficient. Okay, okay, and now let us discuss about the read operation. So one thing to note, that how can you read? You just at any given time, at any given time read the, make your WL equal to 1, read the value of bit line via a sense amplifier. Okay, but what is happening, you understand it very carefully, that whenever you read, C gets discharged. Okay, or C loses its value. This is called destructive read, which was not present in case of your SRAM. Okay, so that is one clear distinction. Another thing is that you know this curve, right? This is log ID versus VGS. So at 0, you know that your I of is not equal to 0. That means transistor is leaky. Okay. So what does a leaky transistor mean? For example, let's say this is your word line, this is your bit line, and you have something connected to this. Suppose you make your WL equal to 0. Okay. Transistor should be ideally off. But then again, I of is flowing through this transistor, should be off, but non-zero I of is flowing through this transistor, right? And let's say if your bit line is grounded, so whatever the value of this C will get discharged through this path. Okay, storage node voltage drops. Okay, so that is not good for us, right? Because below a certain threshold, if suppose your high value is stored at C or the storage node, if it starts leaking after sufficient time, it will read it as 0. Okay, so that will misinterpret the information stored. That is not ideal. So what do we do? A periodic reading writing means you read the data and immediately write back again. Okay, so that the reading writing operation or periodic refreshing is essential. Okay, so that's make this device dynamic. Okay, so that is why it is called dynamic random access memory, because periodic refreshing is required. Refreshing means what? You read the data, write it back so that you maintain the storage node in voltage. Okay, so that is how much DRAM you should know at this stage. There are much more intricate details regarding these capacitances and sense amplification and how reading and writing is done, how we using timing diagrams and other stuffs, but save it for the for your later courses. Okay, so the final topic what I want to discuss today is the scaling theory. Okay, so what is scaling theory? We have seen so far that we want the transistor to get miniaturized. Okay, why the reason? Reason is to increase the ion. Ion increase. First thing is increasing ion. Ion increasing means speed is more. Okay, and also the second aspect is you can integrate more number of devices. So you can fancy better complex designs. Okay, or complex operations through the processors. So was proposed by Robert Dennard we basically will look into three types of scaling theory. Okay, one we call constant field scaling. Second we called constant voltage scaling, and the one which prevailed was hybrid scaling. Okay, that is a combination of these two. So let us lay down the foundations. So we have some primary scaling, you say that primary scaling factors. Okay, what are these? Your channel length, width, TOX, junction depth, okay, and whatnot. These are the metallurgical parameters or the lithographic parameters that you can control. Okay, then you have your Na or Nd doping, right? Let's say K is the scaling factor. Okay, then what? Then we have supply voltage, VDD. Okay, then we'll see other derived parameters. Derived scaling factors, you will have your electric field. Okay, then you will have your IDS, then you will have your capacitance. Fine, then you have your performance. What are your performance? Delay, CV by I or Q by I, then your power, VI, then your power delay product, basically the product of the above two, that is CV square. Okay, so these are the stuff we need to check in what every scaling, what are the scenarios. Okay, so first thing is that in every scaling, be it constant field, constant voltage or hybrid scaling, your dimensions are has to be scaled by 1 over k. K is the scaling factor. For example, if we want to reduce the dimension by 50%, my k will be 2. Fine. Then what about your doping? Why should doping be scaled? Just think for a minute. Why should your doping be scaled at all? Because what is your W depth or the depletion width? Depletion width formula is this by QNA 2 epsilon psi s, right? So your field is not scaled in this case. So your dimension is scaling. Field is voltage by length. So voltage has to be scaled by 1 over k, right? So if all dimensions are scaled, so W depth has to be scaled by 1 over k. You know your size scales by 1 over k. So you have 1 over k in the left hand side, you have root over 1 over k in the right hand side. So you need another root over 1 over k. So that is scaling of this Na. That means you need to scale your Na also by 1 over k. Then only you can scale the depletion width of the MOSFET as well. Okay. So that is why doping is also scaled. Okay. Understand this very carefully. So your doping is in denominator, right? So doping is scaled by K. So it is scaled up basically, not scaled down, it is scaled up. So what about your IDS? Your W by L goes for a toss, and then there you have a voltage square dependency, right? What is your IDS equation? Half mu n Cox W by L VGS minus VTH whole square, right? So this is scaling independent. Your voltage is scaled by 1 over K. So this is 1 over K square, right? And your Cox will be scaled over 1 over K, and area will be K square. So your current also scales by 1 over K, okay? And your capacitances will be scaled by, similarly you should derive these things as well, okay? And check what are the effect of scaling on this product. This you please do as part of your homework, okay? In this case, what is the constant voltage scaling different? Supply voltage does not scale, so your electric field will be increased, okay? And what about your Na and D? Obviously, to keep the your voltage as it is not scaling, so this has to be increased by K square, okay? And what about your hybrid scaling? Hybrid scaling is nothing but you have a factor alpha. Alpha does not have to be equal to K, okay? So your basic scalings, note your alpha is not equal to K. So this is historically what happened? Neither this was strictly followed after some time, so this is what was followed. Okay, so that is basically the types of scaling you have. Also, some key inventions that aided scaling. For example, in 90 nanometer, you had strained silicon. Okay, so compressive strain increase mobility of PMOS. So, for example, let's say we apply silicon, germanium, and silicon. Okay, so your silicon has a 5.43 angstrom lattice constant. Silicon germanium will be something different. Okay, so this will create strain in the bonds. Okay, that changes your mobility and that alters the creates strain, alters the EK diagram, changes mobility. Okay, this is what was done for PMOS case. For NMOS case, silicon nitride spacers were used. Okay, so this is one key invention you should be aware of. Another one is 45 nanometer. They have introduced high K metal gate or high K dielectric metal gate. Okay, high K dielectric means, so what happens if you, let's say this is your gate, this is your oxide, and this is your substrate. So what happens if you reduce your TOX? So if you reduce your TOX, tunneling happens, or in other word, your dielectric starts to act like a conductor. That is not what you want. You want, however, to preserve the field effect. So we want to keep COX intact. Okay, because COX is what determines the field effect. So COX is your epsilon ox by Tox. Okay, and that is your epsilon r time E0 times Tox. So you want what? You want this. You can also increase this and decrease this and also keep your, in other word, you can increase this, keep your Tox, let's say 10 nanometer. Okay, and you can use a different material oxide. For example, not your SiO2. SiO2 has a dielectric constant of what? 3.9, right? You can use, let's say, HFO2, which has a 21 to 25 dielectric constant. So you get a better your this oxides while not compromising on the TOX or the oxide thickness. Remember this thing or understand this thing very carefully that tunneling depends on the physical dimension of the TOX, okay? But this field effect depends on the effective oxide thickness, EOT, what we call it, okay? So that is one invention. Another key invention was your 22 nanometer technology, where FinFET was introduced. This was the idea was there from Professor Chen Ming who is also one of my mentors, Professor Chen Ming from UC Berkeley. Okay, this was one of the most important inventions in this century. Okay, so what he was thinking that why should we have gate on one side? Let us wrap the channel around for from the three side. Okay, so FinFET structure is something like this. So you have, let's say, this is your gate. Okay, and this is your channel, let's say. So on other side it will be something like this. Okay, so you see that the channel, so this is the channel region, right? So this is the channel region, this is your gate, let's say this is your source, this is your drain. So this channel region is wrapped by gate in all three directions. What does it help? It helps in increasing the field effect, okay, rather than diminishing. It increase the effect of gate on the channel more than that of the control of drain and source. Okay, fine. So that is all for today. I will share a link for detailed discussion on this topic. If you are interested. Okay, so just you have to and you should know this stuff, so that's why I have mentioned. Okay, and also in nowadays you can see you have multiple in today's research, you have, you know, fork sheet, nano sheet, gate all around. Okay, gate all around means you wrap the gate from all four sides. Okay, it's kind of like a sheet. The channel is in between and gate is all around. Okay, that is called gate all around or GAA MOSFETs. Then people are exploiting 2D materials, okay, for further scaling down. 2D materials like your MOS2, WSE2, graphene was there. Graphenes are used for contacts, okay. So multiple research fronts are there on this topic, and scaling is still a widely researched topic. And you know that every year international roadmap for semiconductor devices uh, or devices and systems happens, they lay out the foundations for next couple of years or maybe 5 to 10 years research and what the direction the industry should take for this scaling. So if you are interested, you can have a research career in these domains also. Okay, so I think that is a good point to stop today. So we discussed on memories and briefly touched upon the scaling. Okay, thank you.